Okay, we're going to go ahead and start with a warm-up problem. So I would not say you need to worry about drawing the graph. I would just write your answers to these 7 problems, but I'm going to go ahead and give you a couple minutes. Here is the graph of f of x, and I'd like you to evaluate these 7. It looks like there's 6 limits and 1 function value. So I'll go ahead and give you a couple minutes to do that. This can be done in your notes, in your homework. I don't really care where it's done. Just answer these 7. If you need a little bit more time, go ahead and pause. But let's go ahead and go through these answers. So the limit as x approaches -4 of f of x, 1, 2, 3, 1, 2, 3. So here is -4, and it looks like we have a function value right here. So this answer would be -2. Okay, the limit as x approaches 0 of f of x. If we come from the right side versus the left side, these do not meet, so this limit does not exist because the right and the left-hand behavior are different. If we look at the limit as x approaches 2 of f of x, here is x equals 2. It looks like from the right, we have unbounded behavior. From the left, we have unbounded behavior. And unbounded behavior from any side means that we are going to have a limit that does not exist. Okay. The limit as x approaches 1 from f of x. Well, here's x is 1, and here's our coordinate right there. We're just going to go ahead and estimate that that looks like it's about a half for our y value. If you put 3/4, that's fine too. Okay, it's not an exact grid line, and so we can estimate that one there. Here we have x approaches -5. So 1, 2, 3, 4, 5. As x approaches -5, if we drive our car on the curve from right and left, we're approaching that hole, which is at 0. Now I'm going to jump down here to number 7. F of -5 would be where the coordinate is, which is right here at -2. Okay, and then finally, the limit as x approaches 4. 1, 2, 3, 4. Here's 4. We have a coordinate right here, so it looks like that's about 2.5. Okay, 5/2, 2.5, however you want to write it. Okay. Okay, so what we're going to do today is we're actually going to look at solving limits analytically. Okay, so yes, we can evaluate limits on a graph, but what if we don't have the graph? If we have just the equation, can we go ahead and figure out what the limit is? Okay. So I have a couple of graphs that we're going to start with just to kind of get our brains going here. And I want to look at this one right here. This is the graph of y equals -2. Okay. If we talk about the limit as x approaches 2 from this graph. What's it going to be? It's going to be -2, right? From the right and the left. Okay. If we look at the limit as x approaches 0 on this graph, from the right and the left, we approach a y value of -2. Does it matter which y coordinate I'm going to pick here? From the right or from the left, we are always going to have a y value of -2 because we have a horizontal line. Okay, so that's one of the properties that we're going to talk about. Okay, if we have some sort of horizontal line, okay, then it doesn't matter what limit I'm asking you to find. It's always going to be the y value of that horizontal line. So what I just highlighted in orange, that's what I need you to write down. Okay, the limit as x approaches c of b equals b. If we have a horizontal line, y equals b, the limit is just going to be that y value every time. Okay. And we'll come right back to that. What I want to look now is at this right here. Here's the graph of y equals x. Okay, and let's look for some patterns here. If we look at the limit as x approaches, I don't know, let's say 1 of y equals x. From the right and the left, we have a y value of 1. Okay, what about the limit as x approaches -2? Well, here's -2. From the right and the left, we have a y value of -2. Since we have this property, y equals x, okay, the x coordinate and the y coordinate are always the same on this line, which means our limit is going to have that same value. So the next one I want you to write down is right here. The limit as x approaches c of x is just going to be c. Okay, we essentially can plug c in for x in order to get that value. Which also works in this case right here. The limit as x approaches c of x to the n is just going to be c of n. Whatever that number is, we can plug it in for x to get our limit. Okay, now I will tell you, writing down these general rules is way more intimidating than actually going through the problems themselves. Okay, so here are 3 examples I'd like you to write down. Okay, so the limit as x approaches 13 of 5, well, if we just have a constant, that means we have a horizontal line and our y value is the same no matter where we are. So this limit is just going to be that constant, 5. Okay. Here, the limit as x approaches 4 of x, well, remember, that's this line right here. Basically, we're just going to throw this number in for x, so this limit is 4. Okay, Lastly, the limit as x approaches 2 of x cubed, what we get to do here, what we get to do here is throw this in for x, so this is 2 cubed, which is 8. And it's as simple as that. Okay. Now, I will tell you there are some properties that we can talk about here. It is possible for us to multiply by a scalar, add, subtract, multiply. There's some properties that we can talk about. So let's say we have the limit as x approaches c of f of x, and that is some limit L. And we have another limit as x approaches c of g of x, and that's some number k. All right, what we can do, it is legal for us to take the limit of some number times that function, and it's just going to be that number times whatever the limit is. Okay, really that's not going to feel any different. If there's some scalar multiple, we just multiply the limit by it. Okay, same thing happens if we have a sum or a difference inside, like we have two functions added together inside of our limit. We can take those limits separately and then add them together or subtract them. And you are going to probably assume that anyway, but now we've just actually talked about it. Okay, the same thing is going to happen if we have multiplication or division. If we are multiplying two of them, we can simply take their limits separately and multiply them. Or if we're dividing them, we can do the same thing. We just need to make sure that that limit in the denominator is not 0. Okay. So those are just some properties, and those will unfold as we go through some examples. And I think even if I didn't talk about those, you probably would have assumed them anyway. Now, here's where the algebra part of limits gets to begin. Okay. We have this concept of direct substitution, and this is always what we are going to try first if we do not have a graph. Okay, direct substitution is our first analytical step in order to determine if we have a limit when a graph is not given. Okay, so this is important. Okay, if we can't do direct substitution, then basically the remainder of our unit is talking about other strategies that we can use. Okay, so there's a lot of words right here, and this is how it looks in your book, but I'm going to tell you what I want you to actually write down. I want you to actually write down these two things that I'm highlighting. Okay, we're going to talk about the limit of a polynomial and the limit of a rational. And what we have here is essentially saying if we have a polynomial or a rational, whatever we are approaching for our limit, that was a terrible circle, whatever we are approaching for our limit can just be plugged in to evaluate our limit. When we think about the graphs, right, whatever graphs that we've been doing, okay, if I'm looking at this limit and I'm driving my car from the right and the left, we're really searching for the y value of that coordinate, okay? Well, when we're talking about a polynomial, we know that there are no holes in a polynomial. So we are fine to just substitute that c value through, okay? We also know that as long as our denominator is not 0, we don't have to worry about holes or asymptotes of a rational function. So we can do direct substitution with a rational. Whatever we're approaching, we can just throw it in. And as long as our denominator is not 0, we don't have to worry about that. Now, we will talk later what happens if that c value makes the denominator 0, and we have multiple strategies we can use for that. Okay, so let's see what this looks like. Okay, so here I have the limit as x approaches 3 of 3x plus x squared. Okay, in order to evaluate this limit, we're going to take that number right there and we're going to throw it in to our function. So 3x plus x squared. That y value is 18, which means the limit as x approaches 3 is going to be 18. Okay, I'm essentially asking you for the y value that we are approaching on our graph. Okay, let's look at this one right here. The limit as x approaches 3 of 2 over x cubed. Now, 0 would make our denominator 0, but that's not where our limit is, so we don't have to worry. So all we have to do is take that value and throw it in. So we have 2 over 27, and that is the limit as x approaches 3 of 2 over x cubed. Okay. The same thing can also be done if we have radicals. Okay, we can also use direct substitution with radical expressions. So here we have the limit as x approaches 3 of the square root of 3x squared. Since we're approaching 3, and 3 is in the domain of this guy, then we can just take it and throw it in for x. Okay. Now, you are in AP Calculus, and the advantage of being in AP Calculus is that I will no longer require you to simplify your answers. So the square root of 27 is perfectly acceptable. So is 3 radical 3. It doesn't matter, but I am not going to take off points if you do not simplify. The AP test doesn't take off points, so Mrs. Homan will not take off points. So welcome to the big show. We have other things to worry about. We're not going to worry about simplifying radicals. Okay. All right. So what happens if direct substitution does not work? What will happen? Okay. So let's look at some strategies. When direct substitution does not work is when we have something like this. I have a rational expression here, and we try direct substitution. All right, 2 squared minus 4 over 2 minus 2. Oh my, we get 0 over 0. And we know that that's not okay. All right, 0 over 0 is not okay. So the 0 in the numerator is not a big deal, but it's the 0 in the denominator right here. Okay, when you get 0 over 0, you know that algebraically there is something that you can do in order to evaluate the limit. Okay, so we kind of talked about this yesterday, but when we have a rational, we know that we can simplify. So our numerator is x plus 2 times x minus 2, which can cancel out with our denominator. So now we have the limit as x approaches 2 of x plus 2, which we can evaluate to be 4. Okay. What's happening there is we have this graph right here. Okay. Our function was x squared minus 4 over x minus 2. And when we went ahead and we simplified that, we knew that there was going to be a hole at x equals 2. So here is that hole. And then the rest is the line x plus 2. Okay, so when we took the limit to find the limit as x approaches 2, we were finding where that hole was. We didn't have to graph to know that it was 4, but graphically this is what's matching up. We figured out that that hole is at y equals 4. Okay, so let me remind you, we got a 0 in the numerator and a 0 in the denominator, and we knew that we could do something algebraically in order to get a number for our limit. Okay, let's look at another example. Okay, and it looks like the same thing is happening. We have the limit as x approaches 0 of radical x plus 1 minus 1 all over x. If we were to actually plug in 0, we would get 0 over 0. Okay, so algebraically, we can do something. Now, I know it's been a while since you've used this word, but anytime we have addition or subtraction with a radical as a piece of it, we can multiply by what's called the conjugate. Okay, a plus b is the conjugate of a minus b. And when we multiply two conjugates together, we get the difference of squares. Okay, that's something that happened a lot in your Algebra 2 and your pre-calculus days. So the conjugate of our numerator would be square root of x plus 1 plus 1. Here's a, here's b. Okay, and whatever we do to the numerator, we also have to do to the denominator. Okay, well, this seems like a mess. Mrs. Homan, where's this going? Okay, when we take our numerator, which is a difference of squares, we get a squared. So radical x plus 1 squared, okay, minus b squared. Okay, well, that's nice because we can take those ones and we can cancel them out. So we have the limit as x approaches 0 of x over x times radical x plus 1 plus 1. And now the x's can cancel. Now we can finally use direct substitution. Since we canceled out in our numerator, we're going to call it 1, and in our denominator, we're going to plug 0 in for x. So what we get is 1/2. Okay, so this strategy, we had a radical that involved addition or subtraction, and so we multiplied by its conjugate in order to help us get something to cancel, and then we could use direct substitution. Okay, so you will have problems like that in your homework tonight. Okay. Okay. Two more things we have left to talk about. The first is a composite function and how we take this limit. And I feel that I probably would not need to go through this with you. This is probably something that could be almost intuitive for you, but I think it would be a good thing to talk about. Okay? So, if we have the limit of a composition, just like with a normal just evaluating a function, we need to work from the inside out. Okay, so the first thing you are going to do is you are going to take the limit of the inside. Okay, so you are going to figure out what the limit is as x approaches c of g of x. Okay, so we can do this one of two ways. You can say, all right, f of, I'm taking the limit as x approaches c of g of x. And that's going to get you a value. And then that's going to become your next limit. So the limit as x approaches whatever that value was of your outer function, f. Okay, so you can continue to take that limit, and then you can use direct substitution. Okay, so let's go through that with this example here. Okay, so I'm going to do the composition limit. All right, the limit as x approaches 2 of f of g of x. So first of all, if I take the limit as x approaches 2 of g of x using direct substitution, that would be radical 2. So now what I have is the limit as x approaches radical 2 of our outside function f. And in order to evaluate that limit, we can just use direct substitution with our function f. Throw in radical 2 for x, and we get 6. Okay. In your bookwork, you'll notice some of these problems, and they'll have multiple parts. Like here, I asked you for the limit of a composition. What if I asked you for the limit as x approaches 2 of f of x divided by g of x? Okay, well, if I asked you to do that, then you would use direct substitution for both. So plug 2 in for f to get your numerator, and then plug 2 into your g for your denominator, and your limit would be 8 over radical 2. And just like I said earlier, you don't have to reduce that. You can leave it unsimplified, which is awesome. Okay, the last thing we're going to talk about, and this brings us back to what we did last week in our pre-calculus work. We worked on the algebra of a difference quotient. We did one in class together, we did a couple in our homework, and then we did one for a warm-up on Friday. Okay, what we're going to do now is we're going to actually take the limit of the difference quotient. Okay, now, before you start writing this down, I want you to look at it. And I want you to notice all of these things right here. Okay, you've probably seen that symbol before, especially if you have been in a physics class. But that triangle X means, we say delta X, we call it change in X. Okay, now when we did the difference quotient last week, you saw those with H's. Okay, I have no problem if you would like to change these to H's instead. I think that is easier to work with, especially as we're getting used to all of the notation and the algebra. So if you want to change these to H's, then I say go for it. Okay, so this is the difference quotient, and we are going to be working with the limit of the difference quotient. Okay, and you're going to have some problems in your homework where I'm going to ask you to do this, and this is where the most intense algebra is going to be in your homework assignment. Okay, so I would definitely encourage you to utilize Calc Chat in tonight's homework to check your answers and your algebra. If you didn't do it last night, go ahead and try it tonight with this. Okay, so this is the function we're going to do, 2x squared plus 1. Okay, so now we have an extra step where we actually need to take the limit and evaluate the limit. Every step you do until you actually evaluate the limit, I better see the limit as h approaches 0. So we have f of x plus h minus f of x all over h. Please make sure you're putting minus f of x. That f of x needs to be in parentheses to make sure you get that subtraction carried through. Okay, so we haven't evaluated the limit, which means I'm going to keep writing it no matter how annoying that it is. So I'm going to go ahead and take x plus h, the quantity squared, and I'm going to take that subtraction through. And now I'm going to go ahead and take that 2 through. Okay, now here's the fun part. We know that the 1's cancel. We can see that the 2x squareds cancel. And what we have left, we see they both have an h in common, so we can factor that out and cancel it with the denominator. So we are left with the limit as h approaches 0 of 4x plus 2h. Now, last week we would have stopped at 4x plus 2h, but now we're actually evaluating the limit as h approaches 0. Okay, so what we're going to do is we're going to use direct substitution, where we're going to actually plug 0 in for h. And notice how I didn't write the limit because I'm finally at the step where I am evaluating the limit. And so the answer to the limit of our difference quotient is 4x. Okay. Since we're evaluating the limit as h approaches 0, those h's should disappear for your final answer. Okay. And remember, before you plug in h, you will always get this denominator to cancel out with something in your numerator. Okay. We'll work a little bit more at the beginning of class with some more difference quotient problems tomorrow. But what I'd like you to do is go ahead and get started on your homework. Don't forget that there's that Calc chat link in Google Classroom, and there is also your textbook, the Chapter 1, linked in Google Classroom.